Okay, welcome back, folks, to this last session. So this morning, I'm going to spend the first session talking about performance issues, which is the last lecture in the session. And then the rest of the day is available for practical sessions. Basically, as long as you want and you're still keen. And just let me reiterate that I'm very happy to look at any code that you're working on with OpenMP or with OpenMP in mind, as well as the exercise sessions. Okay, so it's important to think about performance issues because I think this is a common problem, especially with people who are getting started with OpenMP. So I wrote my OpenMP program, and I checked it gave the right answers. Well, so I'm happy, and then I ran some timing tests, and well, the speed up was a bit disappointing. And so now what do I do? Okay. So most of it's probably been here, or it will happen to you at some point that you find yourself in this situation. So the way I like to think about this, or the way I would encourage you to think about this, is where did your performance go? Okay, and the answer is that it's disappeared into overheads of one sort or another. And that's the way that I like to think about performance problems, is what are the possible sources of overheads? And if you understand what can go wrong, then you have a chance of figuring out what has gone wrong in a particular situation, and that will give you the information, or at least some clues as to how you might go about fixing it. So I'm going to talk what I think of as the 6.5 evils of performance. So these are the 6 main categories of overhead that you can get in OpenMP programs. And actually, this is, again, broader than just OpenMP. This really applies to any shared memory programming environment. I mean, some of the solutions I'm going to give you are OpenMP specific, but the issues are basically these ones. So sequential code, idle threads, synchronization, scheduling, communication, and hardware resource contention are the 6. And there's one minor one, which is the extra half, which is compiler optimization or non-optimization, which I'll mention briefly at the end. So what I'm going to do is take a look at each of those and discuss ways of avoiding them. So just a reminder, please interrupt me by either raise a hand or type in the chat window at any point as we go along and ask questions. Okay, so let's start off with sequential code. So this is quite an easy one to grasp. So because in OpenMP, all the code that's outside of parallel regions, or for example, inside master or single constructs, is sequential code that's being executed by one thread only. So the time that's spent in sequential code will limit the available performance. So that's just simple Amdahl's law type arguments. Okay, so if I have a code and a piece of the code that takes 20% of the original sequential execution time is not parallelized, then no matter how many threads I throw at it, and no matter how efficiently the rest of the code is parallelized, I'm never going to get more than 5 times speed up, because that 20% of the original X time is that sequential time is always going to be there. So the solution is at least conceptually straightforward here. Okay, if there's still significant amounts of sequential code, then you basically haven't finished the job of doing the parallelization with OpenMP. So you need to look into those parts of the code and try to find ways of parallelizing. So if you again, think about so where are the overheads going? Well, what's happening is that you have all but one thread are sitting there idle, doing nothing outside of parallel regions, or if there's a master or single directive. But we can also have idle threads inside parallel regions, and there can be a number of different scenarios that cause this. So one of them is that some threads finish some piece of computation before others. So in other words, there's some load imbalance between the work or the tasks that are assigned to threads, and some threads have to wait for others to catch up. Okay? And in OpenMP, the really common situation is that you end up with threads sitting idle in a barrier at the end of a parallel loop or a parallel region. So this is meant to be some sort of activity diagram or activity trace. So this is supposed to represent the activity of 4 threads with time running from left to right. And so let me get a pointer. So suppose this is the start of a parallel region or loop, and then the blue stuff is threads doing useful computation, but it turns out that the 3rd thread takes longer than the others. And so what happens is that there's an implicit barrier at the end of the parallel loop or the end of the parallel region. So the other threads are finished their work early, and the red bit is the time that they spend sitting idle, waiting in the barrier for the 3rd thread to arrive. Okay, so what can we do to avoid load imbalance? Well, if it's a parallel loop, then clearly we've got the ability to experiment with different schedule kinds and chunk sizes. So OpenMP gives us quite a lot of handles to play with to try and improve the load balance for parallel loops. And remember that you can use schedule runtime to avoid having to recompile if you're doing lots of testing of different schedule kinds and chunk sizes. I haven't covered OpenMP tasks in this course. That's actually part of the advanced OpenMP course that we run. But for more irregular computations, using tasks can be helpful. So this is particularly true if we have irregular parallelism and it's nested parallelism. So if you have computations and have multiple layers of parallelism and you have load imbalance at different layers in the algorithm, then using tasks can be the best solution, because it's very difficult to get load balance correct if you, for example, if you try and use nested teams. So without going into too much detail, the idea here is that if we use tasks, then essentially all we're doing in the OpenMP program is specifying the parallel computations, and the runtime is then supposed to take care of the load balancing for us. And so we're basically saying, okay, these are the available parallel computations to be done, and the runtime will try its best to spread those evenly out across the threads. Just a word of warning, just to notice that it's not always necessarily safe to assume that two threads doing the same number of computations will actually take the same time to execute them. So just because two threads are executing identical pieces of code or are executing the same number of loop iterations, and every loop iteration looks the same but is operating on different bits of data, it doesn't necessarily mean that they're all going to take the same time. And the reason for that is that although they're doing the same number of computations, the time that's actually taken for each thread to load and store data from memory may actually be different if or where that data is actually cached. Another possible source of having idle threads is wherever we have critical sections. Threads can be also idle, for example, waiting to access a critical section. So in OpenMP, that would include critical regions, atomics, lock routines. So again, suppose I have an activity diagram like this, and in the middle of a parallel region or a parallel loop, there's some critical section, which is the green stripy bit. So that's a piece of code which only one thread can execute at a time. So what might typically happen is that even if all the threads happen to arrive at the critical section together, then they have to take turns to execute whatever that block of code is, and therefore there will be some idle time while threads are waiting to get into the critical sections. So what can you do here? Well, various tactics here. You can try to make the critical section as short as possible. So it may well be worth working quite hard to minimize the amount of code that's in the critical section and to optimize that as much as possible, so that the length of the critical section is as small as it possibly can be. OpenMP critical regions are really just a global lock. But you can use critical directives with different names to protect different sections of code that don't need mutual exclusion from each other. It's probably always best to use atomics if possible, and it allows more optimization. So it doesn't guarantee it, but most implementations are pretty good at implementing atomics. So, for example, as we saw in the example with the graph, with the degree of the vertices computation, that if we use atomics, that permits concurrent updates to different array elements, whereas critical does not. Or we might get into using, if atomics is not a good solution, we might get into using multiple locks instead. Okay, so that's sequential code and idle threads. Any questions so far? Hi, Andrew.
Sorry, I pressed the wrong button there.
That's okay, no problem.
With the threads, can you go back a slide? Okay.
This one?
Go back one more. You had a, so that's the one, critical thread. So these threads are running in I'm trying to remember. Is this due to the different threads will be running on different CPU units?
Most likely, yes.
So
That's probably what we're going to arrange.
Yeah.
Yes.
Right. Okay. So you have no real control then over the read writes those threads need to do. So they could be sitting sitting idle whilst they're waiting to read data, and this then determines how long. Well, you can't determine it. You can't really find out, can you, how long it takes for those threads to complete.
So the situation I'm imagining here is that there's a critical section inside the parallel region. So only one thread at a time is allowed to execute that block of code. And essentially, if a thread arrives at the critical region and there's already a thread in it, then it has to wait. Okay, it cannot do. There's no way to no way to make it do anything useful.
Outside of the critical region, where code running in parallel, threads running in parallel, there's also if they're running on separate CPUs, then each of those CPU units are going to be running other threads as well. And there's going to be some sort of, I'm just trying to remember, is it pipelining on CPUs? Where you've got threads that are running and have to be paused whilst some data is loaded or some data is saved. And so whilst they're paused, another thread can run.
Okay, so that
on the CPU. So it'll be the load on the CPU then.
Okay, yeah. So that would be the scenario where we're making use of hardware threads or virtual cores. Okay, so most modern CPUs can support having more than one, have hardware support to allow this kind of thing to happen. So you have more than one thread running on the CPU. Essentially, one thread, you can either have one thread running at a time, and then when a thread, say, stalls waiting for a memory reference, then another thread can run in that gap. Yeah, that's one way the hardware works. I mean, and actually, in most CPUs, what can actually happen is you really get instruction streams from multiple threads actually interleaved with each other. They don't really context switch in a sort of one-on, one-off kind of way.
Right.
They basically they are because you have multiple function units on your CPU, so you have basically superscalar CPUs where you're actually issuing you're not issuing one instruction per cycle, you're issuing several instructions per cycle, and it's actually possible for those for instructions that get issued on the same cycle to actually come from different threads.
Right.
Okay. So
but that does that.
Sorry, go ahead.
Impact on that particular thread.
Right. So most of the time, we tend to find that maybe I'm just going down to facilities. is not worthwhile. Okay, why not? Okay, it's because you have to, in order to make use of that, you have to run more threads. Okay, I'm going to run, if I've got, say, 4 cores, and each core supports 2 hardware threads,
yeah,
then I need to have 8 OpenMP threads running.
yeah,
okay. And most of the time, what you find is that the additional overheads, all the other sources of overhead that I'm talking about here, increase when you go from 4 threads to 8 threads. Right? So your load imbalance gets worse, your synchronization costs get worse, everything gets worse, typically. And those overheads all mostly tend to outweigh any benefit that you get from running 2 threads on the same core. Not always, but that's mostly the case. So typically we tend not to do that very much. There are a small number of applications that will benefit from it, but it's actually quite unusual, because the maximum performance gain that you get from running 2 threads on the same core is not double, right? It's like, in reality, you might get, it's like a 10% gain. So it's very easy to lose that 10% gain just through the other overheads that arise from having to double your thread count.
Okay, thanks very much.
Okay, it's an interesting point, though. Yeah, so it turns out, yeah, that facility does exist in the hardware. For a lot of scientific applications, it really doesn't help. I will talk a little bit about that later on, actually. So yeah, we'll come back to that again. Okay, so my next evil is synchronization, because every time we synchronize threads, there's some overhead, even if the threads are never idle. Okay? Because the threads have to communicate somehow with each other to say, okay, we've all arrived at the barrier. Right? There has to be some communication going on in the hardware to make that happen, and it's actually all done through the memory system. Okay, actually, it's all basically reads and writes of memory locations at the bottom level, but that's not free. And in particular, the way OpenMP is designed, you tend to end up with a lot of barriers, so mostly implicit barriers at the end of parallel regions or parallel loops. And barriers are actually quite expensive, as they, depending on, obviously depends on the number of threads, depends on the runtime implementation and the hardware, but typically we think you're looking at thousands to tens of thousands of clock cycles to execute a barrier. So that's quite expensive. You can do quite a lot of computation in 10,000 clock cycles. And then other kinds of synchronization are not free either. So critical atomics locks, those will cost something, even if threads never wait for each other. Just the actual act of acquiring the lock or doing an atomic operation in the memory is not for free. And nor, for example, is creating or executing a task, because again, that requires some synchronization under the hood between threads to implement that. Okay, so what can we do to try and avoid synchronization overheads? Well, we can think about exploiting the outermost level of parallelism possible, and so that we have as large pieces of computation going on independently across threads before we have to synchronize. So doing basically parallelizing big blocks of computation rather than little ones. That's not necessarily the most easy parallelism to exploit. So depending on the way code is written, the easy parallelism may be actually the innermost loops in some cases. But if if all your parallelism is coming from innermost loops, then you're going to end up with you can end up with a lot of barriers, and those absolutely completely dominating the performance. So you think about trying to minimize the frequency of barriers like that. And say it may not be straightforward. It might, for example, require you to reorder loops. But reordering loops of its own, if loops are indexing arrays, then you can also damage your cache behavior by doing that. So it's not necessarily a straightforward change. And so if you're interested in this kind of thing, the last exercise with the ADI code is a good example of this kind of problem, and you can try to think of a good solution for it. So we do have this ability to get rid of barriers at the end of parallel loops with no wait clauses, but you have to be careful. It's all too easy to introduce race conditions by removing barriers that are actually required for correctness. So you have to think quite carefully about the dependencies if you're going to do that. And again, atomics probably have lower overhead than critical or locks in most implementations. Next one is scheduling overheads. So if we take advantage of the features of OpenMP that allow us to create computational tasks and then rely on the runtime to assign those to threads, then we incur some overhead. And actually, some of that's probably going to be internal synchronization in the runtime, but there'll be other bookkeeping overheads going on as well. So where does this arise typically? Well, it's in the non-static loop schedules and task constructs. So if I have a loop like this, so a loop with 10 million iterations in it, each of those iterations doesn't do very much, or maybe most of those iterations don't do very much work. And then I parallelize it with a schedule with dynamic 1. So basically a chunk size of 1. So that means that every iteration is being scheduled, every iteration is being individually scheduled to the threads. Then that probably isn't going to end well. It can easily end up with the overheads of the loop scheduling completely dominating the cost of the computation here. In this case, what it's really about is getting the granularity of tasks right. So if we're specifying computational tasks, then we may need to think carefully about what's the right granularity of a task. And that may not be the granularity that naturally arises in the code or in the algorithm. And it's obviously it can be a balancing trick. Okay, if we have a small number of very expensive computational tasks, so the granularity is too big, then we may well end up with idle threads. because there isn't enough parallelism, or the load balance isn't good. On the other hand, if we end up with lots and lots of tiny tasks, then we might get very good load balance, but we also incur lots of overheads for scheduling those all those tiny tasks. So there's often some sweet spot or compromise in the middle somewhere, where the granularity is big enough to generate enough tasks to keep all our threads busy, but not so big that the scheduling overheads dominate. And you might need to experiment or parameterize that quite carefully in an application in order to be able to get that right, and make it right depending on your input data or the problem that you're solving, and the number of threads that you're using. Okay, so next one is communication, and in many ways this is the most difficult one to both to think about and to solve if it's a problem. Okay. So what am I talking about with communication here? Well, on shared memory systems, communication between threads is, so we've got threads running on different cores, and they need to exchange some data with each other. That appears as increased memory access costs. Okay, because it takes longer to access data that's either in main memory or in another processor's cache than it does to get data from the local cache. So that's how communication turns out to appear. That's where it actually appears in the when you run the code, is that when you run in parallel, some memory references take longer than they did when you ran sequentially. And memory accesses are expensive on modern hardware. So we're talking about order of 100 clock cycles for a main memory access. Can be 200 even, that kind of number. Compared with how long does it take to do a floating point operation? Well, it's a small number, one, 2, 3 cycles to do a floating point operation, say. Or how long does it take to get data from the level 1 cache? 1 cycle. So communication between processes takes place via what's called the cache coherency mechanism. And so this is what's implemented in the hardware to make sure that even though you have lots of separate cache memories, then you still have the illusion that, when you run the program still supports the illusion that there's only ever one copy of anything in the memory, or one valid copy of any data in the memory. So this is quite different from dealing with communication in message passing programs, because in shared memory, this communication is very fine-grained. Okay, it's at the level of individual memory accesses, and it can be spread throughout the program in unpredictable ways or hard to predict ways. So it makes it much harder to analyze or monitor than it does in message passing. Because you can just look at a message passing program and ask the question, where's the communication taking place? Well, the only time it can take place is where I have calls to the message passing library. And it's also possible to design tools that instrument all the calls to the message passing library. So you can get tools that tell you exactly how many messages were sent, when they were sent, how many bytes they all transferred, and so on. So it's possible to get really good performance diagnosis for message passing. Much harder for memory accesses, because they're so fine-grained that instrumenting them is difficult. And also, if you look at a shared memory program and ask where's the communication taking place, well, actually you can't tell. It's very hard to look at a program and say a priori which of those memory accesses, which of those loads and stores is going to result in a cache miss. It's incredibly hard to tell that just by looking at code. Okay, so cache coherency in a nutshell. Okay, cache coherency is quite complicated, but as programmers, we can get away with having a very highly simplified view of what's going on. We don't need to understand all the gory details. Essentially, what's happening is this process here. So whenever a thread writes a data item, it will get an exclusive copy of that data stored in the local cache on the core where that thread's executing. And when it does that write, any other copies of that data item that happen to be in other caches at the moment, those get invalidated in order to avoid other cores from reading out-of-date values or an out-of-date value of that memory location. And then subsequent access to that data item from other threads must get the data from wherever the exclusive copy is. And that's what takes the time, because it takes time to move data from one cache to another. So that, but again, depending on the hardware, that may be going through main memory, or it may be going direct. It depends on the hardware design, but essentially, again, you don't really need to know. Okay. So it's that subsequent read that costs. Well, actually, the invalidation process costs something as well. So the write is also affected in terms of performance, because of the need to contact or communicate with other caches to do the invalidation. Okay, so this is a very highly simplified description of what's going on in the hardware. The gory details are very complicated. But that's essentially what you need to know, is that if we have multiple threads accessing a data item and not all the accesses are read accesses, so at least some of them are write accesses, then there is some additional cost involved in order to allow the cache coherency mechanism to do its thing. So what does this mean? Well, this is really just another dimension to data locality and data affinity. It's something. So data locality is something that we need to care about for sequential programs. We need to make, modern hardware forces us to, for good performance, make efficient use of cache memory. And this is essentially just another dimension to that. So if we're in a multi-threaded context, the data is going to be cached on the processors or cores which are accessing it. So we have to reuse that cached data as much as possible. And in the context of multi-threading, what that means is we need to write code with good data affinity. What does that mean? Well, it effectively means to ensure that the same thread accesses the same subset of program data as much as possible. Okay. So in shared memory, we don't need to do any explicit decomposition of our data. Okay. It all just lives in the shared memory. But nevertheless, we still need to think a little bit that way, to think about not just about dividing up computations, but also think about how those computations are accessing our memory, the data in the program, to try and make sure that, as far as possible, the same thread keeps accessing the same data as much as possible. And again, need to try and make these subsets of data sufficiently large. We can't have interleaved access at too fine a level, and I'll explain why that is in a minute. This is also part of the reason why, or the main reason, in fact, why it's important to try and prevent threads from migrating between cores while the code is running. Okay. So your operating system is prone to try to move threads around to balance out the load across your hardware. Okay. So if you have some cores that are idle and some cores which are, which have heavily computationally loaded, then the operating system will try to balance that load out by moving threads or processes from heavily loaded cores to lightly loaded ones. But whenever that happens, then when a thread migrates from one core to another, it then has to drag all its data, or all its recently accessed data, across with it from the cache where it used to be running to where it is running now. Okay, so essentially, migrating threads tends to result in a whole load of cache misses, because the thread is no longer running on the core that's attached to the cache where it was recently running and where it was storing all its recently used data. Okay, so Chola, so caches are retained across different parallel regions. Yeah, absolutely. Okay, so essentially, the hardware knows nothing about what's going on in your program. Okay, so certainly just because you happen to end a parallel region doesn't mean that the cache data goes away. Okay. So yeah, very much the so I mean, you need to specify the thread number in order to get the right cache. No, that's, as long as you're as long as your threads don't move, then everything's going to be fine. Okay? Because the way the hardware works is that the data will be stored in the cache where that thread is running. So as long as the thread keeps running on the same core, then it'll be accessing the same cache. And the access to caches is completely transparent. Okay, there's nothing that you can do in your program to influence which caches are being used or where your data is being stored. Okay. There's absolutely no way that you, there's no way that you can influence that in the program. Okay, the hardware just implements its hardware algorithms for caching, and you have to deal with it. Okay, so the hardware's trying to do the right thing for you, but There's absolutely nothing you can do to influence what it does. Okay, let's take a look at this example. It might help understand a little bit what's the sort of thing that can go on here. Okay, so we've got a code with 2 loop nests in it. So what I want to do is, so I want to focus on the second one first. Okay, so if we look at the structure of the loops here, we have for I equals 0, I less than n, and then we have j equals 0, j less than I. Okay, so if we parallelize the outer loop, the I loop here, using a parallel for directive, then this is a badly balanced loop because the amount of work depends on the value of I. Okay, so the number of iterations of the inner of the J loop depends on the value of I. Okay, so for small values of I, will be not much work, and then it just basically increases linearly with the value of I. So we need to take care of that load imbalance by choosing an appropriate schedule. And suppose we do some experiments and we say, okay, a static schedule with a chunk size of 16 is appropriate and does a good job of balancing the load. Okay. Then let's look at the previous loop here. Okay, so in the second loop, the loop is accessing these elements of this 2-dimensional array A. There's an access, there's a read of Aij in the second loop. The first loop nest is the one that actually previously wrote the values of Aij. But in this case, the loop structure is different. Here we have I equals 0, I less than n, and j equals 0, j less than n as well. So this loop is well balanced. So you know, at first glance, there's no reason to use anything other than static schedule. In fact, we typically might not even specify a schedule clause at all. Might just go with the default. Then think about what's happening here is that when we come to run this second loop, for any given element of A, so for a given Aij, then for most of them, the thread that's doing the read here is not the same thread that did the write here because of the different schedules. So almost all of these reads here are going to have to result in some communication between the caches. Because the write here will cause the elements of Aij to be stored in the cache close to the, or attached to the core where the thread that did the write was executing. We come to the second loop. For most of these accesses, then they're coming from a different thread because of the schedule clause, and therefore this data is not stored in the local cache where that thread is running. So the fact we've got these different access patterns in these two loops mean that we incur quite significant communication costs here. So in this case, there would be a fairly easy fix. Okay, we could simply apply the same schedule to the first loop as we have for the second, and then the access patterns all match up nicely, and then indeed we then guarantee that the thread that reads AIJ was the same thread that previously wrote it. Here's another example, the same sort of thing. Okay? So suppose we have a parallel loop that reads values from some array A. We then have the next loop is then not parallelized. Okay, it's outside of it's part of the sequential part of the program. So this will be executed by the master thread, and then we repeat the first loop again. So again, if we execute this sequence of code, this sequence of loops, then let's think about what happens to these values in A. Okay. So when these reads happen, then we will get bits of A spread across multiple caches because we've divided this loop up between different threads. When we execute the writes sequentially, all those copies in other caches will get invalidated, and the cache where thread 0 is executing will end up with the exclusive copies of all of A. And then when we come to read A again, then these accesses then have to go and fetch those copies from the cache where thread 0 is executing. And what you will see in practice is that not only does this loop take longer than you expect, or doesn't speed up as much as you might expect, you can also find that because of the invalidations going on, that this loop takes longer if we're executing with multiple threads than it did when we were executing sequentially, even though this loop is not parallelized. So as you can see, reasoning about this is quite tricky. Okay, so again, this is saying I'm simplifying. I'm kind of assuming that A fits some level of cache. We have in the hardware, we have multiple levels of cache. We have some of those caches are shared between threads and some not. Right? So there's a lot of complexity, and it's very difficult just to stare at a piece of code and say, aha, these accesses are going to be cache misses and others are not. Okay, yeah, so yeah, I think I've probably gone over this. Yeah, the sequential code will take longer with multiple threads than it does on one thread because of the invalidations going on, and the second parallel region will scale badly because of the additional cache misses. So this is okay. What we might need to do here is that you may end up needing to parallelize code which doesn't appear to take very much time in the sequential program. Okay, you may have sort of decided that that this loop wasn't worth parallelizing because it doesn't really account for very much time in the sequential program. But because that decision results in bad data affinity, you might actually be better off parallelizing it, or possibly even better in this kind of case, merging these two loops together and parallelizing the resulting merged loop. Okay, any questions about that? Okay, so as if that wasn't bad enough, there are other things to do with communication, other effects which are also very nasty. Okay? First of these is number effects. So what does this mean? Okay, so NUMA stands for non-uniform memory access. Okay, and it relates to this idea that, or the fact that in real hardware, we don't just have one monolithic block of memory. The memory is actually inside a node. The memory is actually divided up. So in a lot of systems, if we have, for example, a lot of HPC systems these days have 2 processors per node. Okay, so 2 chips per node, where each of those chips is multi-core. And so each chip comes with its own memory. Some newer systems like ARCHER2, then even the memory that's attached to a single chip is divided up. So on ARCHER2, there are 2 chips per node, but the memory attached to each chip is actually divided up into 4 sections. And each of those 4 sections is essentially tightly coupled to 16 of the cores. So this type of system, then actually the location of data in main memory is important. And OpenMP doesn't give you any way of controlling that. So it doesn't give you any support for saying, okay, here I'm going to allocate some large multidimensional array. Please either make sure that it's all on one block of memory, or that it's somehow distributed in some way across multiple blocks of memory. You can't do that directly. What typically happens is that, so the operating system makes some decision about, whenever a program accesses a piece of memory, which physical block of memory is that actually going to get stored into. And the common default policy, so at least in Linux, like Linux operating system, or Linux variants, is to place the data, okay, on the processor, or in the memory attached to the processor which first accesses it. Okay. So whichever core makes the first reference to that piece of memory in your program, that memory will get allocated in the block that's closest to where that first to the core where that first reference came from. So this is called the first touch policy. And so for a lot of applications, and particularly for message passing type applications, that's absolutely the right thing to do. Okay, that's a very sensible policy, because you pretty much guarantee that if you have separate processes running and they're bound to cores, then that's if the first reference to that data comes from that core, then you can be pretty much guaranteed that all subsequent references will also come from that same core, because they're all going to come from the same process, which isn't going to move. For multi-threaded programs, that's not true. And in fact, this default policy can actually be the worst possible case, because what can happen is that your initialization of all your data happens in the master thread. Okay, it's not parallelized. So what happens is all your data gets allocated in the block of memory close to where thread 0 is running. And then having all the threads accessing data in that same block of memory becomes a bottleneck. Okay? What you're effectively doing is you're restricting the available memory bandwidth to one block of memory instead of all of the blocks of memory, instead of the bandwidth available across all the blocks of memory in the node. How do you avoid this? Well, some operating systems you do have some options to control this first touch policy or to change it. So, for example, in Linux, you can use the numactl command to change the policy, for example, to round robin. So it'll just spread. It'll spread all the memory across all the available NUMA regions. The other thing you can do is to make use of the first touch policy indirectly by parallelizing your data initialization. Okay, so that might seem completely useless in terms of the time it takes. Okay, so you might have an application that runs for hours, and the bit at the beginning that initializes your data may take a few seconds. So it might not, from a point of view of the execution, for the overall execution time, you might think, well, absolutely, there's no, I really don't need to parallelize my data initialization. But that initialization will influence where that data is stored in main memory throughout the whole lifetime of the program. So it might be worth doing. It can be difficult, though you don't have to get the distribution exactly right. And in fact, in many applications, there isn't necessarily one right solution for how your data ought to be optimally distributed anyway. But at least some distribution is usually much better than none at all. So just avoiding this worst case scenario where all your data ends up in one NUMA region. You need to just remember, if you're doing that, then the allocation is done in units of operating system pages. So these is typically several kilobytes of memory at a time. And okay, it's a reason not to use to use large pages, not to use megabyte-sized pages. Andrew.
Yeah, can you just go back to the previous slide?
Yeah, sure.
So I'm just trying to picture this in my head. If I've got a large 4-dimensional array that I need to initialize as part of a program, and all I'm doing is just setting all the values to 0, for example.
Yeah.
Are you saying that better that, I mean, that could be done sequentially, but rather than doing it sequentially, split that up as a parallel task?
Yeah, put a parallel, just use a parallel for directive to do it.
Yeah. Right.
For example. Yeah.
So how do I know, looking at the size of the pages that you were talking about at the bottom there, do I have to keep in mind the amount of memory that I'm going to allocate?
No, it just means that you can't parallelize small initial. You can't parallelize small bits of your initialization very easily. Okay, and expect this to work. Yeah. Okay, you have to be, you have to have different threads accessing kilobytes of. You have to have different threads accessing different blocks of data, which are multi-kilobyte in size, for this to work.
Right. Okay.
Right?
So
if you did your
if you
initialized your multi-dimensional array and you did it one column at a time in parallel, that wouldn't work. Okay. For example, it wouldn't have the desired effect, because probably each individual column fits inside a page. So, and that page can't get split up.
Right. So the chunk size for scheduling that parallel task then is tied to the page size. Yeah,
you would need to choose. I mean, typically, if it's a big array, then just parallelizing the outer dimension, right, parallelizing the isolation across the outermost dimension would be absolutely fine.
Right. Okay.
So, which is probably what you would do naturally, right? So it's kind of the natural thing the natural way you would do it would work just fine.
Okay. Thanks.
In that case, yeah. So this is, for multi-dimensional arrays, this is, parallelizing your data initialization is usually pretty straightforward. Okay. It's, if you have more complicated data structures, so if you have an algorithm that's based on trees, or some other kind of irregular data structure that gets dynamically allocated in small pieces, or or kind of organically grown as the program proceeds, then this gets much more difficult to do. But if your main data structures are big multi-dimensional arrays, then this is a pretty easy thing to do. Usually. Okay. Last bit of real nastiness is false sharing. Okay. So now I'm going back to thinking about, not about pages, but the cache coherency, where pages live in main memory. Now back thinking about the cache coherency mechanism again. Okay. And the extra piece of information that you need to understand this is that the units of data on which those cache coherency operations are done is typically something like what's called cache lines or cache blocks. So this is basically the amount of how much data gets loaded at a time from memory into the cache. And the answer is it does it in blocks of typically 64 or 128 bytes, that kind of size. And the important thing is that block size is always bigger than a single word of data. Okay, so your words of data, your integers, your array elements are if they're integers or floating point, then they're going to be typically 4 or 8 bytes. So the problem here is that if you have different threads writing to neighboring words in memory, that can still cause this cache invalidation process to get triggered. Okay. So even though logically there's no communication going on in your program, okay, no race conditions, no communication, I have different threads which are writing to different data items, but they happen to lie next to each other in memory, then this cache coherency protocol can still get triggered. Okay, and it's still a problem if I have it's a problem as long as not everything is a read. One thread's writing and other threads reading, then you can still have problems. Like I said, it's very, very evil. Modern hardware is getting better at handling this, or at least mitigating some of the worst effects of this in the hardware. So it's possibly not as terrible a problem as it used to be. Okay, so the things that you need to look out for here is essentially where you have different threads repeatedly writing neighboring array elements. That's the most likely situation where you're going to run into this problem. Okay, so if you do something like, if, for example, you're inside a parallel region and you want to have a shared array and you're counting something on every thread. Okay, so use my thread number to index a shared array and do something to it, and write values into it, say increment it frequently. Okay. So something like that will cause this problem, because I have different threads writing to neighboring elements in that array. Those elements happen to lie in the same cache block, so that block will always, every write will always cause all the other copies of that block in other caches to get it invalidated. Another kind of situation you might see it is, for example, a loop nest like this. Okay, so we've got two-dimensional loop nest here. So I0, I less than n, and J0, J less than I. Okay, so we've got one of these imbalanced loops again, and the innermost loop writes values into BI. Okay, and we want to parallelize the I loop here. So again, you might look at it and think, okay, it's imbalanced. Let's do a static schedule with a chunk size of 1. Okay. Because that's going to give me the best, or should give me good load balance. But then what are the implications of that for the memory accesses? Okay, so it means that consecutive values of I will be scheduled to different threads. So I'm going to end up again in this situation where different threads are writing neighboring elements of B. Okay, so B0 is going to get written by a different thread from B1, different thread from B2, and so on. So again, you can end up with this problem here. What's likely to happen here is that if you then say, okay, if I do some experiments with the chunk size, then you will find that you will find that 1 is not the optimal here. Okay, you'll find that some larger chunk size is better, where I've reached a point where, obviously depending on the type of B here, then all the accesses to a cache block come from the same thread if the chunk size is big enough. So I might need to make my chunk size might need to be 8 or 16 or something like that for that to happen. So you can quite often observe that in some cases the small chunk size does not give you the best performance, and this is one possible reason why that might happen. Whew. Okay, so yeah, communication is tough to. It's tough. Communication problems are tough to diagnose and tough to solve typically. So the last of my 6 main evils is hardware resource contention, because the design of shared memory hardware is a cost versus performance trade-off at some level. Okay, so I mean you could always design better hardware, but it would cost more to implement. So manufacturers don't do it. So that means that there are, in practice, there are shared resources on the chip, which if all cores try to access them at the same time, don't actually scale. Okay. Or if you want to know, that's the glass half empty point of view. The glass half full point of view is that an application running on a single core actually gets access to more than its fair share of the resources. Okay. So that's the way the hardware is designed. Okay. So it means if you're not using all the cores, then some of those resources are then available to the cores which are running something. The resources that we have to tend to think about here are the most important ones are which cores and therefore the threads which are running on those cores can contend for are basically memory bandwidth, cache capacity, and functional units. If functional units, if we use SMT, so simultaneous multi-threading. So that's the idea we were talking about that Andrew was talking about before. The idea of running more than one OpenMP thread per core. So if we do that, then we may also contend for the, for example, floating point units. The most important one, though, is memory bandwidth. And the bottom line here is that codes which are very bandwidth hungry, and that's quite a significant proportion of scientific applications, are indeed very memory bandwidth hungry. They will not scale linearly on most shared memory hardware, no matter how efficiently you're programming them. So this is not a limitation of OpenMP or any other multi-threading API. It's purely a limitation of what the hardware is capable of. The only thing you can really do in this case is to try and reduce the bandwidth demands by improving locality, improving the reuse of data in your application. So reuse the data that gets cached as better. Okay, so that should also benefit your sequential performance as well, but it's especially important for multi-threaded code. Okay, so try not to bombard you with too much data, but I think this is just a very instructive example. Okay, that just shows you just how severe this problem is or how big an effect this is in modern hardware. Okay, so this is some experiments on ARCHER2. So this is the AMD Rome processor. And I'm restricting so this is all done within one NUMA region, okay? So I'm just looking at this group of 16 cores with its attached memory. Okay, so no nasty NUMA effects going on here. Okay. So each of those cores has a level 1 and level 2 cache, and then there is a shared level 3 cache of 16 meg, which holds 16 megabytes of data. And there's one of those for every group of 4 cores. Okay. And I was using, for completeness, I was using the Cray compiler here. And basically, I was executing this parallel loop. Okay. So the fact that it's got a reduction on it is really neither here nor there. It's just basically a loop which does reads to elements of an array. That's the important thing here. Okay. So what I did was run this on for different values of n. Okay, from small arrays up to very, very big ones, and then see how much speed up do I get by varying the number of threads that are executing. Okay. and I'm repeating the execution of this loop enough times to make sure that if the first time effect of data getting into the cache for the first time is not significant. Okay, so if data is going to be cache resident, then basically if it's small enough to sit in the cache, then effectively that's the regime that I'm measuring is basically when if data does fit in the cache, then it will be there. Okay, so I end up with a rather messy graph. So let me try and explain what's going on here. Okay, what am I actually plotting? Okay, so I am plotting the speed up that I got, okay, versus the number of loop iterations. Okay, so that's the value of n in that. Okay, so just number of loop iterations, just the value of n in this loop. Okay. So I started off at n equals 1,000 and go up to whatever this is, 10 million. And say, okay, do this for different numbers of threads and calculate the speed up compared to running on one thread. Right, so this is a bit messy, but let's just pick out the main features here, okay? Let's start off by looking at the blue curve here, which is 2 threads. Okay, so I start off for n equals 1,000 by getting almost no speed up at all. Okay, and that's true, in fact, for all numbers of threads. So what's going on at the bottom level here is that I just don't have enough work in that loop to be worth parallelizing. Okay, so this is basically the idea that, going back to the idea that you have to have enough computation inside a loop to overcome the overheads of starting a parallel region and stopping the parallel region and synchronizing the threads. Okay, so it turns out that I need of order of tens of thousands of loop iterations just to break even here, okay, to get to a speed up of 1. So that's what's happening at the bottom here, okay? So I call death by synchronization here, okay? So it's basically the cost of synchronizing the threads at the end of the loop, and also doing the reduction to some extent as well is completely killing me for small values of n. But for 2 threads, once I've overcome that, then eventually the speed up, at some point, the speed up reaches a value of 2 and stays there. So if I'm just running 2 threads, then provided there's enough work, then I have enough memory bandwidth to keep feeding those 2 threads. But even if I go to 4 threads, something different happens. Okay? So again, once I've overcome the synchronization costs, I do at some point just about reach 4 times speed up, but then it drops a bit to something just over 3 for a while, and then eventually it drops back to something that's only just over 2. Okay, so what's happening here is that at this point, then the data, the array, so basically in this region here, the array fits in the level 3 cache. And the bandwidth to the level 3 cache isn't quite enough to keep all my 4 threads busy. And then at this point here, the data doesn't fit in the level 3 cache anymore. So all those memory references, all those reads are coming directly from main memory. So then I'm now contending for memory bandwidth. So as long as my data is big enough, then I can never achieve, no matter how many threads I run, I barely get more than 2 times speed up. And this is what's happening here, okay? For large nodes, I'm simply, the essentially, or look at it the other way around, one thread can get about half the available memory bandwidth on this NUMA block of NUMA region of memory, and anything more than 2 threads will saturate the whole memory bandwidth. And in the middle here, for other thread numbers, you get some weird effects, because so for example, if I go to 16 threads, yeah, I get this big jump. And what's happening here is that at this point, I'm benefiting from the extra level 3 cache capacity. Okay? So by running 16 threads, I have 4 times the available level 3 cache capacity compared with running 1 thread. Okay? So at this point here, on 1 thread, the data doesn't fit into 1 level 3 cache, but it does fit into the 4 level 3 caches that these 16 threads are spread across. So at this point, I actually get slightly more than 16 times speed up for a small window of data sizes. So that's really quite complicated. You can see that these modern chips have the memory systems are pretty complicated, and you can get lots of quite strange effects going on with them. But I say, bottom line is, okay, look at this. Look at the right-hand end of the graph. Okay, this is where the performance is completely controlled by the main memory bandwidth. Okay, so you can also contend for cache space. Okay, if we've got shared caches, then codes may not scale very well, because when we run a single thread, that has access to the whole of the shared cache. And then when we start running multiple threads, then they have to share that cache space. Okay, so we've already talked a bit about hardware threads, but so just to recap here. Okay, so if we use hardware threads, so we have multiple OpenMP threads running on the same core, then they will contend for the functional units. So things like particular floating point units. Okay, so say most application cores don't benefit from you doing that. The ones that do are ones where threads are likely to be idle because they're waiting on memory references. So codes with new non-contiguous or sort of pseudo-random memory access patterns. Large sparse matrix computations, for example. However, codes which are bandwidth hungry or which saturate the floating point unit, so if we're doing dense linear algebra, doing matrix-matrix multiplies, for example, they may actually not, they don't benefit from using hardware threads, and typically may actually go slower because of all the other overheads associated with having to have additional having to double the number of OpenMP threads that you're running. The other way you can the other way you can get into trouble is by by going beyond what the hardware can support. So running more threads than you have hardware execution units, whether that's cores or hardware threads, is generally a bad idea. Because what happens then is that you don't have enough cores to have all your threads actually executing at the same time, and the operating system will try to give each thread a turn and give them a fair share of the hardware execution units. And the cost of stopping one thread and starting another, okay, if it's the operating system that's being involved, is high. It's an order of thousands or tens of thousands of clock cycles. And as also talked before, it ruins your data locality, because it typically means that threads are not bound. You can't have your threads bound to cores. So because you don't have enough cores to bind them to, so you're likely to end up with threads being thread that's running on one core will get stopped, and then the next time it runs on a different core, and all your cached data is in the wrong place again. Okay, any questions about that? Okay, so I mentioned 6.5 evils. So what's the half? Okay, so the half is a rare event which hopefully will never happen to you, but it's just worth being aware that it is possible, and that's to do with compiler optimization. Very occasionally, adding OpenMP directives to your code can prevent the compiler from performing some sequential optimizations. Okay, doesn't often happen, but once in a while you might get really unlucky and have this happen to you. Okay, and the main symptom of that is that if you run the parallel code on one thread, you see a longer execution time than running the sequential code. If this happens, it's pretty nasty because it can be very hard to find a workaround. It can be very hard to figure out what it is that the compiler, in terms of the optimization, that the compiler is failing to do and why. Can sometimes be changed cured by making relatively minor changes to the code that just stop this happening. So things like making shared data private, or making local copies of variables that are passed in through the argument list might help. For example, one that I've seen involved was actually it was a Fortran code, and so if you pass, so I'm sure Fortran programmers will know, but for other folk, if you pass a Fortran array into a subroutine, then you can either pass just the name of the array, or it's legal and equivalent to pass the first element, to actually specify the first element of the array. And there was a code that happened to do that as for no particularly good reason, just a programming quirk. It was passing the first element of arrays around instead of the array name, and for some reason for GNU compilers, that broke the optimization, and adding OpenMP directives just made the sequential code go sort of twice as slow for certain loops. What can you do? So just weird stuff. Just be aware that if you see that kind of thing going on, then if you're adding OpenMP suddenly makes your sequential code go a lot slower for some reason, then this is most likely what's gone wrong. But it can be pretty hard to figure out why. Okay, so just to finish off with some strategic thinking here. Okay, so you're in this situation where your code isn't giving you good speed up, and you don't know why. Okay, so what do you do? Okay, so don't go down number one. I would say, okay, don't just say, okay, OpenMP is rubbish and give up. Okay, try to do something. Go through some logical process. So what I think is the logical approach here is to try and classify and localize the sources of overhead. Okay, So if you can understand that, then you have a good chance of fixing it. So what type of problem of it? Which of the 6 evils, or possibly more than one of them, is hurting you, and whereabouts in the code is that happening? So if you can determine that, then you are in with a fighting chance of being able to improve the performance. Use tools that are available to you, so timers, possibly hardware counters, profiling tools can be useful. And try and, obviously, same as what you would do for optimizing sequential code, fix the problems which are responsible for the large overheads first. Okay, so it's no point fixing small problems if the big problems are still there. Okay. And then go around again. Once you fix the biggest problem, then ask yourself, okay, what's the next worst problem? What type of problem is it? Where in the code does it occur? What can I do next? Okay. So just a word about tools here. I'm not going to go into really any detail, but just to say that standard profilers, things like standard Linux gprof, or the kind of profilers you get in IDEs, your sort of favorite development environment, can end up being pretty confusing for multi-threaded code, because what they typically do is just accumulate the time spent in functions across all the threads. Okay, so that's okay, but it can be quite difficult, make it quite difficult to interpret, and it also kind of losing you any information that might to do with, say, load imbalance or idle threads. It says they don't tell you about that. Okay, because the information that some threads spent longer in some function than others just gets lost. You can get a lot of useful information by using timers. Okay, so one thing you can do is say, okay, you can add timing calls around every parallel region, and also around the whole code, or at least the main part of the computation that you're interested in. That at least allows you to work out, do the localization. Okay, you can then compute speed up for every individual parallel region, so you can find out which ones have the bad speed up. Okay, and again, you say you can then, if you know the time for the code and you know the time for all the parallel regions, by subtraction you can work out how long is being spent in sequential code. Okay. And basically, don't necessarily assume that that's not going to change from the sequential code, because it might. Okay, there's quite a lot of tools out there, depending on what's available on the systems that you're using. So on ARCHER2 we have ARMMap and CRAPAT and Scalaska available. So other systems may vary. Some of these are, obviously Intel V2 is Intel hardware specific. Other ones are, cost money. Some don't. Okay, so Scalaska, for example, is free and I won't say easy to install, but not a complete nightmare to build for yourself. And it's one that I actually like, because it if you do full tracing experiments in Scalaska Scalaska handles OpenMP quite well. Okay, and it does things like it does try to break the overheads down into different categories. So it tells you about things like load imbalance and idle threads and synchronizing, time spent in synchronizing in barriers. So it does do a reasonable job. Unfortunately, the thing that almost all of these tools cannot do is tell you very much about communication or hardware resource contention, so memory bandwidth contention, for example. However, there is this tool called Thread Spotter, which works in a different way, and is actually much better at dealing with cache and memory issues, including things like fault sharing, for example. Oh, okay. That was probably fairly intensive and exhausting, so I apologize for that. Does anybody have any final questions before we have a break?